You begin by letting your thoughts grow quiet, like dust slowly settling in a sunlit room. There is nothing you need to solve right now, nothing you need to hold together. Only a gentle invitation to feel the ground beneath you, and to imagine that it is not still, not frozen, but slowly alive. You rest your awareness on the earth below your body. Not just the floor, not just the soil or stone, but the whole layered planet beneath you. Miles of rock. Rivers of minerals. Ancient heat. You picture it not as a hard shell, but as something more like a sleeping giant, breathing in a rhythm too slow for hurried eyes. The earth has a pulse. Not a quick one like your heart, but a deep one. A patient one. A pulse measured in thousands and millions of years. If you could watch mountains with time-lapse vision, you would see them rise like bread in an oven, then soften and fold back into the crust. If you could listen with a geological ear, tuned to deep time, you would hear continents drifting like slow clouds across a molten sky. Beneath your feet, far below the crust where cities and forests rest, the planet is warm. Warmer than any desert day. Warmer than any summer air. The deeper you imagine traveling, the more the temperature rises, not suddenly, but steadily, like descending into a long, glowing evening. This warmth is not accidental. It is the leftover fire of Earth's formation, and the quiet energy of radioactive elements slowly transforming in the dark. Tiny atomic changes release heat, grain by grain, moment by moment. A planet-sized lantern glowing from within. You can think of radioactive decay like a field of microscopic candles, each one flickering as it changes form. No single candle is strong. But together, across unimaginable volumes of rock, they keep the deep earth warm and restless. Rock, under enough heat and pressure, does not behave the way you expect. It does not always stay rigid. Given time and the earth has plenty of time, solid stone can flow. Not like water, not like oil, but like very thick honey moving in slow motion. A motion so slow that a fingernail grows faster, yet motion all the same. You were taught as a child that rock is firm and final. But deep below, rock is patient and flexible. It bends. It creeps. It circulates. This is the first gentle secret of volcanoes. They are not sudden intruders. They are surface expressions of a deep and continuous conversation inside the planet. Imagine placing your hand near a sleeping animal and feeling the warmth through its fur. Volcanoes are like warm places where the Earth's inner heat comes closer to the surface. Not always erupting. Not always dramatic. Often simply present, a reminder that the inside is warmer than the outside. Most of the time, this heat travels upward very slowly, conducted through rock grain by grain. But sometimes it gathers. Sometimes it finds pathways, fractures, weak zones, ancient scars in the crust. Through these, melted rock can begin to rise. This melted rock is called magma when it is underground. Lava when it reaches the open air. Two names for the same glowing material, defined only by where it is in its journey. You picture magma now not as a violent force, but as a traveler. Thick. Buoyant. Patient. Rising because it is slightly lighter than the rock around it, the way warm air rises through cooler air. Physics, not anger, guides it upward. Pressure and density, simple rules, shape this movement. Nothing rushed. Nothing emotional. Just natural law unfolding at its own unhurried pace. Volcanoes, then, are not Earth's outbursts. They are Earth's vents. Like pores on skin. Like openings where inner warmth can slowly release. Some volcanoes build tall mountains over many eruptions, layering lava and ash like careful brushstrokes. Others spread wide and low, pouring fluid basalt across great distances. And some, the rarest, do something different entirely. But those giants sleep deeper in our story, waiting for later chapters. For now, you simply sit with the idea that the ground is not dead matter. It is process. It is motion slowed to a tempo that feels like stillness. You breathe in gently, and as you do, you imagine the planet breathing too. Not in air, but in cycles. Heat rising. Crust shifting. Mantle turning over itself like a slow ocean made of stone. The mantle, the thick layer between Earth's crust and core, is not liquid like the outer core, but it is not perfectly solid either. It behaves like warmed wax under pressure. Over millions of years, it circulates. This circulation helps move tectonic plates above it, those vast puzzle pieces that carry continents and seafloors alike. You float for a moment on that image, continents like rafts, riding on deeper currents. Your worries feel smaller here. Your deadlines dissolve. Deep time has a calming effect. Nothing hurries at this scale. Even the most dramatic eruptions are brief moments in a very long symphony. A volcano may erupt for days, months, even years, and still be only a single note in a score that lasts 10 million years. Seen this way, eruption is not constant threat, but rare punctuation. Between eruptions, there is listening, gathering, adjustment. Rock warms. Crystals form. Gases dissolve into molten material like bubbles waiting in dough. Systems balance and rebalance. Scientists who study volcanoes often speak of them the way doctors speak of bodies, watching signals, measuring changes, learning normal rhythms. Pressure, chemistry, motion all leave signatures. The Earth, in its way, keeps records through patterns. And you, tonight, are simply learning how to listen. You listen not with instruments, but with imagination. You feel the layered planet as a living structure. Crust like skin. Mantle like muscle. Core like a deep, glowing heart of metal. Not alive in the biological sense, not made of cells, but alive in motion, in change, in energy flow. Planets cool over time. That is another gentle truth. Earth was once far hotter, more molten, more chaotic. What you live on now is a calmer version, slowly releasing its ancient heat into space. Volcanoes are part of that cooling process, small windows through which inner warmth escapes. So when you think of a volcano, you can picture not only fire, but balance. Regulation. A pressure valve in a planetary system. You rest with that image, balance, not violence. Release, not rage. Your breath slows. The planet's breath slows with you, or perhaps you are slowing to match it. Either way, your sense of time stretches comfortably. Minutes feel wide. Thoughts drift like ash settling on quiet ground. And as you lie here, held by gravity, warmed by a distant core you will never see, you may begin to wonder if heat rises, if stone can flow, if pressure can open pathways upward. Then what is happening right now, quietly, in the deep places below, where fire moves in darkness, preparing stories the surface has not yet learned to read? You let your awareness drift downward now, as if your thoughts are feathers settling through layers of air, then soil, then stone. There is no falling sensation, only a gentle passing through. You move in imagination, not body, and so everything is calm. The surface world grows quiet above you, winds, oceans, forests, all becoming distant, like sounds fading at the end of a day. Below the ground you first meet the crust, the thin outer shell of the planet. Thin, at least, compared to what lies beneath. Under continents it can be as thick as a mountain range is tall, and yet compared to Earth's full size, it is like the skin of an apple. You picture that apple now smooth, delicate, and realize how shallow most of human life truly rests. The crust is broken into plates, great stone rafts that drift slowly over deeper layers. You already sensed their motion in the last chapter, the slow rearranging of continents. But now you move below those plates, into a region of increasing warmth, where pressure grows like a heavy blanket laid gently, then steadily, then firmly over everything below. Temperature rises with depth. On average, about 25 to 30 degrees Celsius for every kilometer you descend in the upper crust. Not everywhere the same, but steady enough to feel like a rule of thumb written in heat. You imagine a thermometer stretching downward, its red lines slowly climbing as you travel deeper in your mind. At first, the rock is still solid and brittle. It cracks under stress. It holds faults and fractures like old scars. But deeper still, under greater pressure and temperature, rock changes behavior. It becomes less like a biscuit and more like wax. Less likely to snap, more willing to bend. This is not because it melts completely, but because minerals inside it begin to soften at their edges. Crystals shift. Boundaries slide. Given enough time, even solid rock can flow, not in seconds, not in hours, but across thousands of years like a glacier made of stone. You arrive now at the upper mantle, the vast layer beneath the crust. It extends down for hundreds of kilometers. It is hotter here, and pressure is immense. If you could stand here, which you cannot, the weight above would feel like entire mountain ranges pressing on your shoulders. And yet, under such pressure, melting does not always happen easily. That is one of the quiet surprises of geology. Heat alone does not guarantee melting. Pressure resists it. Like a tightly closed lid on a boiling pot, pressure can keep material solid even when it is very hot. For rock to melt and form magma, something must change. Temperature rises further, pressure drops, or water and gases mix in to lower the melting point. These are the three gentle keys of melting: more heat, less pressure, or added volatiles. You can think of volatiles as chemical helpers, like salt sprinkled on ice to make it melt faster. In subduction zones, where one tectonic plate slides beneath another, water trapped in minerals is released downward into hotter rock. This addition helps generate magma, a subtle chemical invitation to soften. Now you begin to picture magma not as a giant underground lake, but as pockets and zones of partial melt. Small at first. Scattered. Like beads of warm syrup forming inside a thick loaf. Melt gathers between solid crystals, finding connected pathways, joining neighbors, slowly increasing its fraction. Magma is usually less dense than the solid rock around it. Only slightly, but slightly is enough. Just as warm air rises through cool air, less dense melt tends to rise through denser surroundings. This is buoyancy, the same principle that lets a wooden boat float and a bubble climb through water. You watch in your mind as melt begins to migrate upward through tiny channels. Not a river. Not a rush. More like seepage. Grain to grain. Boundary to boundary. A patient rearranging of position driven by density and gravity. Some melts stall and cool before going far. They crystallize again, becoming intrusive rock, frozen below ground. Granite bodies deep in the crust are often the cooled remains of ancient magma that never reached the sky. Quiet endings to upward journeys. But some melt continues. It collects in reservoirs, magma chambers, though the word chamber can be misleading. It is rarely a single open cave of liquid. More often it is a sponge-like region of crystals and melt mixed together, a mush zone with variable pockets of fluid material between solid frameworks. You imagine this magma mush like a jar of thick porridge, where grains and liquid share space. Over time, new injections of hotter melt can enter from below, adding heat and material, stirring the system. Crystals may grow, sink, dissolve, or change composition. Chemistry evolves slowly, like flavors blending in a long-cooked stew. Gases are part of this mixture too: water vapor, carbon dioxide, sulfur compounds dissolved under pressure in the melt. Like carbonation in a sealed bottle, they remain hidden while pressure is high. Their presence matters. They influence melting temperature, magma viscosity, and eruption style later on. Viscosity is simply resistance to flow, how easily something moves. Honey has higher viscosity than water. Cold honey higher than warm. Magma viscosity depends on temperature, crystal content, and silica percentage. Basaltic magma, lower in silica, tends to flow more easily. Rhyolitic magma, higher in silica, tends to be thicker, stickier, more reluctant to move. You don't memorize this. You feel it. Thin magma flows like warm syrup. Thick magma moves like peanut butter slowly stirred. As magma gathers, pressure builds, not like anger, but like accumulation. New melt arrives. Gases remain dissolved. Surrounding rock confines the space. The system adjusts continuously, seeking balance between input and release, heating and cooling, expansion and containment. Most of the time, balance holds. That is another calming truth. For every eruption you have heard about, there are countless magma bodies that cool quietly underground, never breaking the surface. The deep earth is active, yes, but also patient. You rest with that patience now. Activity does not always mean drama. Movement does not always mean danger. Much of nature's most important work happens slowly in unseen: roots growing, mountains weathering, crystals forming in darkness. Scientists learn about these hidden regions through indirect signals. Seismic waves change speed depending on what they pass through. Melt slows them slightly. Gravity measurements shift with density differences. Electrical conductivity rises where fluids and melts exist. It is like mapping a dark room by listening to echoes and feeling warmth through walls. No one drills down to magma chambers directly; they are too deep, too hot, too pressurized. Instead, understanding grows from patterns, experiments, and careful inference. Knowledge assembled like a mosaic from small, careful pieces. You float in that mosaic now: heat, pressure, chemistry, motion, all interacting in a choreography that never rushes. Fire beneath the crust is not chaos. It is process. It is physics given time and space to express itself. And as you continue downward in imagination, feeling the warmth increase and the rock grow softer in behavior, you may begin to wonder about the rare places where these deep reservoirs grow: unusually large, unusually rich in melt and gas, unusually powerful places where the planet stores far more energy than a simple volcanic mountain requires, and those places are waiting for a different name. You continue your quiet descent through understanding, and now your attention widens. You are no longer looking at a single plume of rising magma or a lone volcanic peak. Instead, you begin to sense scale: not height, not drama, but volume. The kind of scale that belongs to reservoirs, to regions, to systems that stretch wider than horizons. When most people hear the word volcano, you notice the same image appears: a mountain with a crater, a cone with a plume, a peak that stands apart from the land around it. It is a vertical image, tall and pointed, like an exclamation mark written on the landscape. But a supervolcano does not usually look like that. A supervolcano often hides in plain sight. It may appear as a broad basin, a gentle depression, a landscape of rolling hills and lakes. You could stand inside one and not realize you are inside anything at all. The drama is not in the shape above ground. The story is in the volume below. So you gently shift your mental picture. Instead of imagining a tall cone, you imagine a vast underground reservoir, a region where melt has gathered again and again across long ages. Not a hollow cave of liquid fire, but a sprawling crystal-rich mush zone, fed repeatedly by injections of hot magma from deeper sources. The word super here does not mean hotter. It does not mean more explosive by personality. It means capable of producing an eruption with an extraordinary volume of material, more than 1,000 cubic kilometers of erupted magma and ash in a single event. That is the scientific threshold often used. Numbers that large can feel slippery in the mind, so you translate gently. Imagine a cube of rock 10 kilometers long, 10 kilometers wide, and 10 kilometers tall, then imagine it melted, fragmented, and spread across the sky and land. That is the scale scientists are describing. You do not rush this image. You let it remain abstract, like viewing a mountain range from an airplane, vast but softened by distance. Scientists measure eruption size using something called the Volcanic Explosivity Index, or VEI. You can think of it like a staircase of magnitude. Each step upward represents roughly 10 times more erupted material than the step below. It is not a perfect scale, but it is useful, like a ruler for past events written in ash. Common eruptions that make news might sit around VEI 3 or 4. Historic large eruptions, the kind that affect regions, might reach VEI 5 or 6. The rare giant eruptions that reshape continents reach VEI 8. That top step is where supereruptions live. But again, you keep the tone gentle. A scale is not a prophecy. A category is not a schedule. It is simply a way of sorting the library of Earth's past behavior. You imagine that library now, shelves made of sediment layers, book pages made of ash beds, each eruption leaving a thin signature that travels far beyond its source. Some of the largest eruptions spread ash across whole continents, fine particles drifting in the upper atmosphere before settling like gray snow over distant plains. What makes such an eruption possible is not just melt, but storage and evolution over time. Large silicic magma systems rich in silica tend to be more viscous and more gas-retaining. Over many cycles of recharge and cooling, melt can differentiate, becoming chemically evolved, more resistant to flow, more able to trap dissolved gases. Gas matters because gas expands. Quietly at first, invisibly under pressure, but powerfully when pressure drops. Like opening a carbonated drink after shaking it, rapid decompression allows bubbles to grow fast. In magma, expanding gas helps fragment melt into ash and pumice, driving explosive eruption columns. You picture bubbles rising through thick syrup, stretching, merging, pushing outward. Not violent in your mind, just physical, inevitable, governed by pressure and solubility. A supervolcano system is usually built through repetition. Many smaller magma injections arrive over hundreds of thousands of years. Some erupt modestly. Some stall and crystallize. Each cycle changes the thermal and chemical state of the crustal reservoir. Heat accumulates. Rock weakens. Storage capacity grows. It is like charging a vast thermal battery one careful layer at a time. Importantly, most of these systems spend the overwhelming majority of their existence not erupting. Quiet dominates. Cooling dominates. Crystallization dominates. Even when large reservoirs exist, the fraction that is actually eruptible melt at any given moment may be limited. That is another soft truth scientists emphasize. You let that settle. Presence does not equal immediacy. When a very large eruption does occur, the surface often collapses afterward because so much subsurface support has been removed. The emptied or partially emptied reservoir cannot hold up the roof rock above it. The ground subsides, forming a wide depression called a caldera. A caldera is not built upward, it is formed downward. A landscape that falls inward rather than rising high. Lakes often fill these basins. Forests grow inside them. Life continues, sometimes unaware of the structure beneath. You imagine standing at the edge of such a caldera at dawn. Mist over water. Birds crossing quietly. Beauty resting inside the geometry of an ancient collapse. Catastrophe transformed into habitat across time. Some of the most famous examples exist today as national parks and high plateaus. They are studied carefully, continuously, with networks of instruments, but they are also places where people hike, observe wildlife, and watch sunsets. Dual identity, scientific focus and peaceful landscape. This duality is important for your calm understanding. A powerful past does not erase a peaceful present. Supereruptions are extremely rare on human timescales. The intervals between them are measured in tens or hundreds of thousands of years, irregular, not periodic, not like a ticking clock. Geological recurrence is not a metronome. It is more like weather patterns spread across ages, clustered sometimes, absent for long stretches. Probability exists, but schedule does not. You breathe slowly and hold that distinction. Science measures likelihood, not destiny. It maps possibility, not appointment times. Researchers study crystal growth zones, isotopic clocks, and melt inclusions, tiny trapped droplets inside minerals, to reconstruct how long magma resided, how fast it evolved, how conditions changed before past eruptions. These crystals are like memory chips grown by nature, recording temperature and chemistry as layered patterns. You like this image, crystals as archivists, quietly storing thermal diaries. From these records, scientists learn that many large systems experience repeated recharge, mixing, and partial mobilization before major eruptions. Long preparation. Complex assembly. Not a single switch, but many adjustments. So super does not mean sudden monster. It means large-scale system with deep time construction. You feel the fear word dissolving, replaced by a scale word. Not terror, magnitude. Not threat, process. And as your understanding widens from cone to caldera, from mountain to reservoir, from moment to million-year preparation, you may feel a new curiosity forming. If such vast events happened before, how do scientists read their timing so carefully from quiet layers of ash and buried minerals, and how does stone keep such patient records at all? You step now into a different kind of landscape, not deeper into heat, but deeper into memory. The journey turns from molten reservoirs to quiet records. From fire to traces. From eruption to evidence. You begin to see that the Earth is not only active, it is also archival. Nothing that happens on this planet disappears completely. It changes form, it spreads, it settles, but it leaves signatures. A supereruption does not only release energy, it writes a chapter. And that chapter is stored in ash, in crystals, in layers that wait patiently to be read. You imagine the ground beneath you as a library floor, built from stacked pages. Each page is a layer of sediment, dust, or volcanic ash. Some pages are thick, some thin. Some are smooth and fine as flour. Others are gritty, mixed with tiny shards of glass formed when magma fragments explosively and cools in air. Volcanic ash is not like fireplace ash. It is not soft carbon powder. It is pulverized rock and glass, sharp-edged at the microscopic scale, born from rapid fragmentation. When it falls, it settles across landscapes, lakes, forests, and oceans, forming a time-stamped blanket. You picture ash falling through quiet air like gray snow, spreading far from its source. The thicker the layer in a place, the closer that place once stood to the eruption plume. The thinner the layer, the farther away. Thickness becomes distance's whisper. Over time, new sediments bury the ash. Soil forms. Plants grow. More layers accumulate. But the ash bed remains a distinct stripe in the layered cake of geology. Different in color, texture, chemistry. Scientists call these marker layers. You can think of them like bookmarks placed across wide regions at the same moment in time. If the same ash chemistry appears in lake cores hundreds of kilometers apart, researchers can match them page to page, confirming they came from the same eruption. This matching is called tephrochronology, though you don't need the word. You only need the feeling, matching fingerprints across distance. Each eruption has a chemical signature, shaped by its magma source and evolution. Ratios of elements silicon, potassium, sodium, iron vary slightly from one volcanic system to another. Instruments read these ratios like barcodes. The ash reveals its origin quietly, precisely. You move now from ash to crystals, the tiny timekeepers grown inside magma bodies. When magma cools slowly underground, minerals begin to crystallize. Atoms arrange themselves into ordered structures, forming quartz, feldspar, zircon, and other minerals depending on chemistry and temperature. Crystals grow layer by layer, like tree rings, though often invisible without magnification. Each growth zone forms under slightly different conditions, temperature shifts, composition changes, pressure variations. These zones are chemical diaries written in stone. Zircon is one of the most valued of these mineral recorders. It is small, tough, and excellent at holding certain radioactive elements within its structure when it forms. Uranium is one of them. Lead is not, at least not initially. This matters because uranium slowly transforms into lead through radioactive decay. Not quickly, not unpredictably, but at a steady, measurable rate like a perfectly patient hourglass that never needs turning. When a zircon crystal forms, it locks uranium atoms inside its lattice but excludes lead. From that moment forward, the uranium begins its slow transformation. You smile at the elegance of this. A clock grown by nature, powered by atomic change, ticking across millions of years without winding. Different isotopes, different atomic forms, decay at different rates. Some are useful for thousands of years, others for billions. By choosing the right isotopic system, scientists match the clock to the age of the event they are studying. It is like selecting the right timepiece, seconds, days, or ages. You keep the feeling gentle, clocks made of crystals, hourglasses made of atoms. Rocks can also be dated by the layers above and below them. This is relative dating, understanding sequence without exact numbers. Like knowing that one letter was written before another because it sits lower in the stack. Absolute dating adds the timestamp. Relative dating gives the order of chapters. Lake sediments are especially precious archives for volcanic history. Fine particles settle year by year on lake bottoms, forming thin seasonal layers called varves. Light layers for summer deposits, darker layers for winter, a natural calendar written in mud. When ash falls into a lake, it creates a distinct band within these annual layers. By counting varves above and below, scientists can estimate how many years separate eruptions or how long after an eruption other changes occurred. Counting years like counting rings in a tree, but made of silt and silence. Ice cores hold similar stories. In polar regions and high mountains, snowfall compresses into ice layer by layer. Tiny trapped bubbles preserve ancient air. Dust and ash trapped in the ice preserve distant eruptions. Chemistry shifts slightly where volcanic aerosols once drifted through the sky. A spike in sulfur compounds in an ice layer can point to a major eruption year, even if the volcano stood on another continent. Sky-wide events leave planet-wide traces. You rest in the beauty of this connectedness: eruption, atmosphere, snowfall, ice, all linked in record. None of this reading is rushed. Samples are collected carefully. Contamination is avoided. Measurements are repeated. Uncertainty ranges are calculated and shared openly. Science here is not a shout. It is a careful listening practice. You imagine researchers brushing sediment cores gently, slicing thin rock sections, placing crystals under microscopes, watching isotopic ratios appear on screens. It feels less like hunting and more like translation, turning Earth's quiet script into human language. And through this translation, timelines emerge. Not perfect timelines, not to-the-day precision for ancient events, but increasingly refined histories. Sequences of eruptions. Intervals of dormancy. Patterns of clustering. Rhythms, though never perfectly regular. You feel how this connects back to your earlier understanding. Supervolcanoes are not judged only by what they could do, but by what they have done, measured through these records. Volume, timing, frequency, all inferred from layers and crystals and chemistry. The planet writes slowly, but it writes clearly. You breathe and imagine turning one of these stone pages. A pale ash layer appears between darker sediments. A thin line that once darkened skies. A narrow band that represents weeks of eruption and centuries of consequence. Time compressed into texture. The ground is not mute. It is simply written in a language that requires patience to read. And as your mind grows comfortable with this idea that fire leaves pages, that crystals keep clocks, that ash becomes ink, you may begin to wonder about the great caldera landscapes themselves, still present today, still warm below, still watched the sleeping giants whose past chapters are known, but whose future pages are not yet written. You now rise gently from the layers of record and memory and return to the surface of the earth, but you return with new eyes. Landscapes no longer appear only as scenery. They feel like chapters. Valleys become paragraphs. Rock layers become sentences. And in a few rare places, entire regions become long, quiet epics written by fire and time. These are the sleeping giants, the great caldera systems of the world, places where the crust once opened in enormous release, then settled back into long silence. You might expect such places to look fierce or broken, but often they look peaceful. Wide skies. Forests, lakes. Meadows where animals graze and clouds drift slowly overhead. The calmness can feel surprising, like discovering that a once roaring waterfall is now a still pool. You begin with the idea of a caldera. Not a cone, not a peak, but a basin, a broad depression formed when a large volume of magma leaves the underground reservoir and the overlying rock can no longer support itself. The surface collapses inward, creating a vast bowl-shaped structure. Collapse, here, is not violence but geometry. Support removed, stone settles. You picture it like a loaf of bread whose center is gently taken out from below. The crust above sinks slightly, forming a dip. On Earth, that dip can be tens of kilometers wide. Over time, water may gather there. Rain and snowmelt fill the low ground. Lakes are born. Sediments accumulate. Life returns. The wound becomes a habitat. One of the most studied examples rests beneath a landscape visited by many people each year, a high plateau of forests, rivers, hot springs, and wildlife. Beneath it lies a large volcanic system that has produced several very large eruptions across the past few million years. Today, it expresses itself mostly through heat at the surface, geysers, springs, fumaroles that whisper steam into cold air. Hydrothermal features are like the visible breath of a warm underground system. Groundwater seeps downward, meets hot rock, warms, and rises again carrying dissolved minerals. When pressure drops near the surface, steam forms and escapes. Not magma, just heated water, but still a reminder of the below. You imagine standing near a geyser at dawn. The air is cool. Steam rises in soft clouds. The ground smells faintly of minerals. Nothing feels hurried. Nothing feels explosive. Heat is present, but expressed gently, like warmth from a covered cup. Another giant rests in a large island arc region, where tectonic plates converge and descend. There, repeated caldera-forming eruptions have shaped wide volcanic fields. The land rises and falls subtly over time as magma and fluids move at depth. Instruments measure millimeters of change, the ground breathing too slowly for your eyes to see. You like this phrase, the ground breathing. In yet another region, a chain of ancient calderas stretches across a plateau, marking the track of a mantle hotspot interacting with moving crust. As the tectonic plate drifted slowly overhead across millions of years, volcanic centers appeared one after another, like footprints in stone. Each footprint marks a former focus of heat and melt. Motion above, source below, patterns written by relative movement. Not all sleeping giants are equally warm today. Some are largely cooled, their magma systems mostly crystallized, their heat greatly diminished. Their calderas remain as topographic memory, shape without current fire. Others still host partial melt zones and active hydrothermal systems, watched carefully by scientific networks. Monitoring does not mean alarm. It means attention. You rest with that distinction again. To watch is not to fear. To measure is not to predict disaster. It is simply to listen with instruments. These monitoring systems include seismometers that feel tiny earthquakes, micromovements caused by rock adjusting to stress or fluids shifting in fractures. GPS stations measure ground position with satellite precision, detecting uplift or subsidence as small as a few millimeters. Gas sensors analyze emissions from vents and springs, noting changes in carbon dioxide or sulfur compounds. Each signal alone is like a single musical note. Meaning comes from patterns, chords, sequences, changes over time. You imagine a quiet control room where data flows in like soft music, lines rising and falling, numbers updating, maps glowing gently. Scientists do not sit waiting for explosions. They sit watching trends, comparing baselines, asking calm questions. Is uplift steady or slowing? Are earthquakes migrating or scattered? Are gas ratios shifting or stable? Most of the time, the answers describe background behavior, the normal restlessness of an active planet. Noise, not warning. Adjustment, not crisis. You travel in your mind now across several of these giant systems. Wide calderas filled with lakes. Resurgent domes, areas where the ground has slowly pushed upward after collapse because magma or hot rock remains below, buoying the crust slightly. Lava flows that came later, smaller eruptions that gently resurfaced parts of the basin floor. A caldera is not always the end of activity. It is often a phase in a long story. Post-caldera eruptions are usually far smaller than the Great Collapse forming events. They may build domes or short flows. They are like afterwards rather than main chapters. Time between major eruptions is long and irregular. Hundreds of thousands of years may pass with only hydrothermal activity and minor events. Systems evolve, cool, recharge, and reorganize. Some may never produce another very large eruption again, Possibility is not certainty. This matters for your sense of calm. Presence of a system does not equal imminence of an event. A sleeping giant is defined more by its past capacity than its near-future schedule. You sit with the image of sleep now. Sleep is not death. Sleep is not tension. Sleep is a state of lowered activity, of restoration, of slow internal processes continuing quietly. The analogy is imperfect but soothing. Underground heat flows. Crystals grow. Fluids circulate. But no eruption breaks the surface. Human time passes quickly compared to these cycles. Entire civilizations rise and fall during a single volcanic quiet interval. Languages change. Borders shift. Forests migrate. The magma system below continues at its own pace, largely indifferent to surface history. This perspective stretches your worries thinner. Urgency softens when placed beside deep time. You also understand now that these places are not isolated villains in Earth's story. They are expressions of tectonics, heat flow, crustal composition, and mantle dynamics. Result, not intention. Process, not personality. When you see images of these landscapes, wide basins, blue lakes, steaming valleys, you can hold two truths at once. Beauty above. History below. Neither cancels the other. You breathe slowly and let the idea settle that calm scenery can have dramatic ancestry, and dramatic ancestry can lead to calm present. Transformation is common in geology. Catastrophe becomes contour. Ash becomes soil. Collapse becomes meadow. And as you rest in these wide caldera landscapes of the mind, peaceful yet deeply storied, you may begin to wonder how scientists detect the faint early hints of change in such enormous systems, what subtle signals rise first, what whispers appear in stone in motion before any larger chapter begins to turn. You settle now into a quieter skill, the art of noticing. Noticing small movements. Small changes. Small signals that would be invisible without patient tools and patient minds. After traveling through heat, magma, and vast calderas, you now arrive at listening not with ears alone, but with instruments that extend human senses into the deep. You imagine standing in a wide, peaceful volcanic landscape. The air is still. Birds move through morning light. Nothing appears to be happening. And yet, beneath your feet, the earth is never perfectly still. Rock adjusts. Fluids shift. Heat moves. Pressure redistributes. Motion continues, soft, slow, continuous. Scientists call many of these tiny motions seismic signals. Earthquakes, yes, but not only the large, shaking ones people feel. Most are far too small to notice without sensors. Microearthquakes. Tiny slips along fractures. Minute cracks adjusting under stress. You can think of them as the creaks and sighs of loaded stone. Seismometers are placed across volcanic regions like attentive listeners. Each one rests quietly on or in the ground, measuring vibration with exquisite sensitivity. When the earth trembles even slightly, the instrument records a waveform, a wiggling line that represents motion through time. You picture these lines scrolling gently across screens, like heart monitors for the planet. Different kinds of seismic waves tell different stories. Some are sharp and sudden, produced by brittle rock breaking small fault slips. Others are longer and more rolling, often associated with fluid movement, magma or gas shifting through cracks. These are sometimes called long-period events, soft pulses rather than snaps. You don't need the labels. You feel the difference, crack versus murmur. When magma begins moving into new spaces underground, it can increase local stress and trigger clusters of small quakes. Panic, not panic, but pattern. Scientists look for swarms, many small events grouped in time and space. A swarm is like a conversation, not a shout. It suggests adjustment happening below. But here is the calming truth: most swarms do not lead to eruptions. Rock shifts for many reasons. Heat expands minerals. Fluids change pressure. Faults relax. The Earth is constantly tuning itself. You breathe slowly and let that normalize the idea of motion without outcome. Another signal comes from shape, the subtle rising or sinking of the ground surface. This is called deformation. When magma or hot fluids accumulate at depth, they can push the overlying rock upward slightly, like bread rising as gas expands within it. When pressure decreases, the ground may settle back. The changes are usually small, centimeters, sometimes millimeters, spread across wide areas. Too small for your eyes, but not too small for satellite radar and high-precision GPS. You imagine a network of GPS stations anchored to bedrock, each one knowing its position to within the width of a fingernail. Day after day, they check their distance from satellites overhead. If the ground lifts even a little, the coordinates change. A slow inhale measured from space. Satellite radar adds another layer. It sends signals down and measures how the reflected waves shift over time. By comparing repeated passes, scientists can map deformation patterns across entire regions, broad domes of uplift, gentle bowls of subsidence, like seeing breath move through the crust. You rest with this image, the ground breathing, instruments watching the rise and fall. Heat leaves signals too. Thermal sensors on satellites detect surface temperature patterns. Most volcanic heat is hidden deep below, but hydrothermal areas, hot springs, steaming ground, can change subtly if underground flow paths shift. A warmer patch here. A cooling vent there. Tiny adjustments in the planet's plumbing. Then there are gases, the invisible messengers. Magma contains dissolved gases under pressure, especially water vapor, carbon dioxide, and sulfur compounds. As magma rises or pressure drops, these gases separate and travel through fractures toward the surface. Some dissolve into groundwater. Some escape through soil. Some vent visibly as steam and fumes. Gas monitoring stations sample air near vents and soil. They measure concentration and ratios, how much CO2 compared to SO2, how values change over weeks or months. Ratios matter because they can hint at depth and process. Different gases escape more easily at different pressures and temperatures. You imagine gases like different musical notes escaping from underground, some high, some low, and scientists listening not just for volume but for harmony and change. Carbon dioxide is especially interesting because it can escape from deeper levels than some other gases. Increases in CO2 flux in soil sometimes precede other changes. But again, gently, not as prophecy, but as one clue among many. Water chemistry also carries information. Hot spring fluids dissolve minerals from rock as they circulate. Changes in temperature, acidity, or dissolved elements can suggest shifting pathways underground. Sampling a spring becomes like reading a letter carried up from depth. None of these signals stand alone. That is important for your calm understanding. A single change rarely means much by itself. Interpretation comes from combination, seismicity plus deformation plus gas plus heat plus chemistry. Multiple lines of evidence weaving together. You picture it like weather forecasting. One cloud does not make a storm. One pressure reading does not define a front. Patterns over time create confidence. Volcano observatories around the world operate this way, continuously, methodically, quietly. Data streams in day and night. Algorithms flag anomalies. Scientists review trends. Reports are written in careful language, measured, probabilistic, transparent about uncertainty. Uncertainty is not weakness here. It is honesty. You let that feel reassuring. Science does not pretend to see the future perfectly. It describes what is measurable now and what has happened before. It updates understanding as new signals arrive. It is a conversation with nature, not a command over it. Sometimes signals increase and then fade. Swarms quiet. Uplift slows. Gas returns to baseline. Systems settle again. Many episodes of unrest end in rest. These are called failed eruptions or aborted intrusions, magma that moved but did not reach the surface. You like that phrase, movement without eruption? Effort without outcome. Adjustment without catastrophe. It reminds you of thoughts that rise and fall in your own mind at night. Not every surge becomes action, not every pressure becomes change. Systems release tension in many ways. You imagine the global network now, thousands of instruments across many volcanic regions, all listening. A planetary stethoscope pressed gently against the crust. Data traveling through cables and satellites, arriving as numbers, lines, and maps. Listening at this scale is an act of care. Attention is a form of protection. And as you grow comfortable with these quiet signals, tremor, uplift, gas, heat, you begin to see that the underground speaks in patterns, almost like a language made of motion and pressure. And you may find yourself wondering how scientists learn to translate that language when magma itself begins to move and write its own sentences beneath the stone. You rest now in the idea that the earth speaks, not in words, not in sounds you can hear with your ears, but in patterns. Gentle patterns. Repeating patterns. Subtle variations in motion and heat and pressure. And like any language, this one is learned slowly, through listening over long time. Magma, when it moves, leaves traces. Not footprints, but signatures. Not sentences, but rhythms. Scientists learn to recognize these rhythms the way a musician learns to recognize melody inside vibration. You imagine the underground world again, dark, warm, under great weight. Magma does not rush like a river. It advances, pauses, spreads, cools, reheats, mixes. Its movement is shaped by rock strength, by fractures, by density differences, by available pathways. It is guided, not wild. When magma pushes into new cracks, it forces rock aside. This creates stress changes. Stress changes create tiny slips. Tiny slips create seismic signals. So movement becomes vibration, and vibration becomes information. Some of these signals appear as earthquake swarms, which you already met, clusters of small quakes grouped closely together. But when magma or pressurized fluids move through narrow passages, they can also produce something softer and more continuous, volcanic tremor. Tremor is like a sustained hum instead of a sharp knock. You picture the difference between tapping a table once and slowly sliding your finger across it. One is a click. The other is a tone. Tremor looks like that tone on a seismogram, wavy, continuous, sustained over minutes or hours. It often reflects fluid motion, gas, magma, or hot water traveling through constrained spaces. Not proof of eruption. Not a guarantee of ascent. Simply motion made measurable. You relax into that neutrality. A signal is not a verdict. It is a clue. Another part of magma's language is deformation, which you have already felt as the ground's slow breathing. But here you look more closely at pattern shapes. Different sources create different surface responses. A shallow intrusion may produce a tight uplift bulge. A deeper, broader source may lift a wide region gently. Scientists use mathematical models, soft geometric shapes like spheres, sheets, or lenses to approximate where pressure sources might lie underground. These are not literal balloons of magma, but useful simplifications. Like sketching the outline of a cloud to understand its mass. When new magma intrudes as a thin vertical sheet, called a dike, it can push the ground sideways as well as upward. GPS stations shift directionally. Radar maps show elongated deformation zones. Shape becomes message. You think of it like reading posture instead of words. The way someone stands can tell you what they are doing even from far away. Heat flow adds another dialect. Rising magma transfers heat into surrounding rock and groundwater. Heat changes how fluids circulate. New hot pathways open. Old ones close. Springs appear where none existed before. Snow melts faster on certain slopes. Infrared images show faint thermal halos. These changes are rarely dramatic at first. They are gradients, not spikes. But trends matter. A steady increase across multiple measurements draws attention like a slowly brightening star. Then there is chemistry, the accent of the language. As magma evolves underground, crystals form and remove certain elements from the melt, changing what remains. When fresh magma injects into an existing reservoir, mixing occurs. The chemical composition of erupted or emitted material can reveal this mixing, like hearing two voices blended into one. Even before eruption, gases escaping at the surface can shift in composition when deeper magma contributes new volatiles. Ratios change. Isotopes differ. Each variation is like a pronunciation change that hints at where the speaker comes from. You smile at the thought, accent is depth indicator. Crystals carried upward in small eruptions or gas bursts also contain zoning patterns that reveal their recent environment. A crystal might show a rim grown rapidly in hotter, less evolved magma surrounding an older core formed in cooler conditions. A two-chapter history written in one grain. Scientists slice these crystals thinner than paper and study them with microscopes and lasers, reading element maps like weather maps. Bands, gradients, edges, all telling of movement, recharge, and storage time. Motion recorded in mineral color. But here is the soft, steady truth woven through all of it: the language is complex. No single phrase means the same thing every time. A swarm may mean magma rising or simply tectonic adjustment. Tremor may signal fluid flow, hydrothermal, not magmatic. Uplift may come from gas pressurization, not melt intrusion. Each signal has multiple possible translations. Context decides meaning. You find comfort in this complexity. It prevents rash conclusions. It encourages patience. Interpretation happens through combination and history. What has this volcano done before? How do current signals compare to its past unrest episodes? Are multiple signal types changing together, or only one? Is the system accelerating or stabilizing? Volcanology is less like reading a switch and more like reading weather, pattern recognition, probability, revision. You imagine a scientist listening to weeks of data the way a doctor listens to a long heartbeat record, noting variability, baseline, anomaly. Healthy systems are not flat lines. They are living lines with texture. Magma movement also interacts with rock strength and feedback loops. As rock fractures, permeability increases, more pathways open, which can reduce pressure locally and slow further fracturing. Other times, sealing occurs as minerals precipitate from hot fluids, closing cracks and allowing pressure to rebuild. Opening and sealing like breathing pores. Nothing moves in isolation. Everything responds. Computer models help explore these interactions. They simulate heat transfer, fluid flow, stress change. But models are not predictions carved in stone. They are thought experiments expressed in mathematics. Tools for exploring if rather than declaring when. You keep the tone gentle again. Models are maps, not destinies. Field studies add ground truth. Geologists map ancient intrusions now exposed by erosion, frozen dikes and sills that show how magma once traveled through crust. These are like fossilized sentences of the magma language, preserved where time has removed the covering pages. From them, scientists learn typical shapes, branching patterns, stopping points. They see that many intrusions never reached the surface. Most magma journeys end quietly underground. That is the majority story. Major eruptions are the minority punctuation. You breathe slowly and feel how that shifts emotional weight. Quiet endings are common. Loud endings are rare. So the language of magma movement is rich, multi-layered, and probabilistic. It speaks in tremor and tilt, in gas and heat, in chemistry and crystal zoning. It rarely shouts first. It usually murmurs. And as you grow more fluent in these murmurs, in this patient underground dialect, you may begin to wonder why, even with so many instruments and translations, the exact timing of the largest eruptions still resists certainty, why the clock of supervolcanoes refuses to tick in regular beats, and why prediction, here, remains such a careful art of maybe. You arrive now at a gentle paradox. You have learned that scientists can listen to the Earth's whispers, tremors, uplift, gases, heat, crystals, chemistry. You have seen how many instruments watch, how many records exist, how many patterns are known. And yet, when the question becomes precise, when exactly will a supereruption happen, the answer grows quiet again. Not because no one is paying attention. Not because the signals are ignored. But because natural systems at this scale are layered, nonlinear, and deeply variable. Prediction, here, is not like reading a clock. It is more like reading clouds. You imagine forecasting the weather 1 year from today, at one exact hill, at one exact hour. Even with satellites, models, and centuries of data, such precision slips away. The atmosphere is too sensitive, too interconnected, too dynamic. Small differences grow into large divergences over time. Now you gently translate that idea underground. A supervolcanic system is like weather made of rock and heat instead of air and moisture. Pressure, chemistry, crystal content, fracture networks, fluid pathways all interacting. Each factor influences the others. Each changes with time. Many cannot be measured directly at depth. You sit with that complexity without tension. Complexity is not danger. Complexity is simply richness of interaction. One challenge is that most of the important processes happen kilometers below the surface, where direct observation is impossible. No camera looks into magma reservoirs. No probe sits inside evolving crystal mush zones. Understanding comes from indirect signals, echoes, distortions, emissions interpreted through physics and comparison. It is like diagnosing the workings of a clock sealed inside a box by listening to faint ticks through the wood. Another challenge is variability between systems. No two large magma reservoirs are identical. Composition differs. Crust thickness differs. Tectonic stress differs. Water content differs. A pattern observed at one volcano may not apply cleanly to another. You imagine doctors treating different patients. General biology is shared, but individual history matters. Baseline matters. Response differs. Time itself behaves irregularly in these systems. Recharge of magma does not occur at fixed intervals like a train schedule. It depends on deeper mantle melting rates, crustal pathways opening or closing, previous intrusions heating or sealing routes. Pulses arrive unevenly. Gaps stretch unpredictably. Some large systems show clusters of eruptions close together in geological terms, then remain quiet for hundreds of thousands of years. Others produce smaller events scattered across long spans without ever reaching supereruption size again. Sequence is not rhythm. History is not metronome. You breathe slowly and release the expectation of periodicity. There is also the matter of thresholds, the point at which a system shifts from contained to eruptive. Thresholds in nature are rarely single numbers. They are ranges influenced by multiple variables. Pressure must exceed strength, but strength changes with temperature, fracturing, and alteration. Gas content must reach exsolution, but solubility changes with depth and composition. You think of snow on a mountain slope. One more snowflake can trigger an avalanche, but only when many prior conditions have aligned: slope angle, layering, temperature gradient, cohesion. The final flake is not the true cause. It is only the last contributor. Eruptions follow similar threshold behavior. Many preparatory steps may occur without eruption. Intrusions happen and stall. Gas accumulates and escapes gradually. Rock fractures and reseals. The system circles near thresholds without crossing them. So scientists speak in probabilities and scenarios rather than dates. They build event trees, branching diagrams of possible outcomes with estimated likelihoods based on current data and past behavior. Not prophecy, structured uncertainty. You picture a tree drawn in soft pencil, branches labeled with possibilities, continued unrest, intrusion without eruption, small eruption, larger eruption. Each branch has a weight, but none is certain. The tree updates as new signals arrive. Computer simulations explore ranges of behavior under different assumptions. If recharge rate increases, what happens? If permeability drops, what happens? Thousands of model runs produce envelopes of outcomes, not one line, but a cloud of lines. A cloud of futures. This may sound less satisfying than a single prediction, but it is more honest and often more useful. Decision-makers can prepare for ranges better than for false precision. Preparedness lives well with probability. Another difficulty lies in signal overlap. Many precursors to large eruptions resemble signals produced by much smaller or non-eruptive processes. Seismic swarms occur without eruption. Deformation episodes reverse. Gas spikes fade. False alarms are common, and calling them false is not failure, it is part of cautious interpretation. You remember, movement without eruption is common. Adjustment without catastrophe is common. There is also signal masking. Hydrothermal systems, hot water circulation near the surface, can generate strong seismic and gas signals unrelated to magma ascent. They are like loud surface conversations that make it harder to hear the deeper voice. Distinguishing hydrothermal noise from magmatic signal requires careful analysis and multiple data types. Data itself has limits. Instruments fail. Coverage is uneven across the world. Some large caldera systems are well monitored, others are remote with sparse networks. Satellite data helps fill gaps, but resolution and revisit times still matter. Uncertainty enters not only from nature, but from measurement. You feel how science responds to this, not with despair, but with layered methods. Redundancy. Cross-checking. Independent teams. Open data. Peer review. Overlapping techniques reduce blind spots, like using many small lanterns instead of one bright beam. Communication style also shifts under uncertainty. Alert levels are staged, descriptive, conditional. Language matters. Words like possible, likely, unlikely, elevated, background, these are probability words, not drama words. They are chosen to guide response without exaggeration. You find that soothing vocabulary designed to inform, not alarm. Supereruptions add another layer of difficulty because they are so rare. Statistical prediction works best with many examples. But in the global geological record, only a limited number of VEI 8 scale eruptions are known. Sample size is small. Patterns are suggestive, not definitive. It is like trying to predict the behavior of a rare animal seen only a few times in history. You learn what you can. You avoid overconfidence. Crystals again help refine timescales. Diffusion profiles, how elements spread within crystal zones, can reveal how long magma sat at certain temperatures before eruption. Sometimes the times are surprisingly short, decades or centuries, between final recharge and eruption. Other times longer. Variability persists. So even with crystal clocks, the pre-eruption window is a range, not a timestamp. You rest in the humility of this science. Humility is not weakness. It is alignment with reality's texture. Prediction, here, becomes layered, long-term probability over tens of thousands of years, medium-term assessment during unrest episodes, short-term forecasting when multiple signals accelerate together. Confidence increases only when signals converge and intensify coherently. Like many instruments joining the same rising melody. And still, exact timing remains elusive because thresholds, pathways, and feedbacks interact in ways too detailed to measure fully. The Earth keeps some variables hidden. Not out of secrecy, but out of scale. You breathe slowly and let the need for exact dates soften. Preparedness does not require perfect foresight. Awareness does not require certainty. Science, in this realm, is a practice of respectful listening, updating, refining, revising, never claiming total control, always improving understanding. And as you accept that prediction is mist-edged rather than sharp-lined, you may begin to feel curious about the times in deep history when these rare thresholds were crossed, when supervolcanoes did erupt, and the world quietly changed under drifting veils of ash and altered skies. You now float backward through time, carrying with you the understanding of patterns, signals, and the patient rhythm of Earth. Your journey is no longer downward into the crust, nor outward across the modern caldera landscapes. It moves sideways, across millennia, into history recorded quietly in stone, ice, and sediment. Here, you encounter the moments when supervolcanoes stirred the planet in ways both subtle and profound. Imagine standing on a quiet plain, centuries before humans would tread there. The land is familiar yet strange. Forests stretch in green waves. Rivers meander with gentle patience. The sky is a calm canvas of blue and light clouds. And beneath it all, deep below, a massive reservoir of magma shifts and swells, slowly, persistently, in its invisible chamber. Then, the change begins. Not as a sudden shout, but as a long, measured release. Rock fractures. Magma ascends. Pressure grows, then a threshold is passed. The earth exhales, and the exhalation is vast. Ash rises into the sky. It drifts across continents, softening sunlight as it spreads. Imagine the sun filtered through a delicate gray veil, warmth dimmed, shadows muted. Temperatures fall slightly, not as disaster at first, but as gentle adjustment of climate. Days feel cooler. Seasons shift imperceptibly. Light itself seems softer, slower. Rivers carry fine ash, sediments form in lakes, forests catch thin layers on leaves and soil. Every part of the environment records the event in its own way, storing subtle messages for future eyes to read. The world becomes both the stage and the archive. In oceans, microscopic plankton respond to changes in temperature and sunlight. Growth slows in some regions, accelerates elsewhere. Food webs adjust quietly. Ecosystems ripple with the change, like concentric waves from a stone dropped in still water. Life continues, adapting, shifting, transforming. You imagine observing from above, the plume spreads across the sky, drifting on wind currents. Ash settles in patterns that scientists would one day trace in cores taken from distant lakes and sedimentary basins. Layer by layer, each eruption leaves a signature, a fingerprint for those who learn the language. Ice cores, drilled millennia later from Greenland and Antarctica, preserve this memory in fine layers. Snow compresses into ice, trapping microscopic ash and gas bubbles. Sulfur spikes signal the arrival of volcanic aerosols. Carbon dioxide shifts hint at changes in atmospheric chemistry. Tiny inclusions, invisible to casual glance, tell volumes about the events of the past. You breathe slowly and let the enormity of this history settle. You do not feel fear. You feel connection. You sense how intertwined life and geology are, how changes in one domain softly ripple into another. In some cases, supervolcano eruptions were so large that sunlight was significantly dimmed for years. Summer warmth faltered. Crops failed. Populations of species adapted, migrated, or declined. Ice ages could be nudged or accelerated. Yet even in these periods, life persisted, recovering, reshaping, adapting. Transformation rather than annihilation is the pattern. You picture the Yellowstone supervolcano tens of thousands of years ago. You picture Toba in Indonesia, around 74,000 years ago, releasing ash and aerosols high into the atmosphere. These events, though enormous, are known through the layers and chemical signatures left behind. You can read them today, across time, like letters from the deep past. Human ancestors experienced some of these changes without understanding the cause. They witnessed cooler years, ash on the ground, skies dimmed. They adapted their behaviors, migration, shelter, resource management, guided by observation and experience, not prediction. Life persisted through adjustment, not foresight. You imagine this adaptation as a quiet echo of patience. Nature acts. Life responds. A balance is maintained, though temporary shifts may feel dramatic. The rhythm is slower, larger than human scales, but perceivable to careful eyes and minds. Volcanic deposits preserved in rock and soil tell another part of the story. Thick ignimbrite sheets, deposits of hot, fast-moving pyroclastic flows, cover landscapes far beyond the caldera. Within them, fragile fossils may be preserved, bones and plants baked yet recognizable, each a snapshot of an ecosystem at the moment of the eruption. Even devastation leaves record, and record preserves memory. Magma chemistry, crystal content, and isotopic ratios in these deposits allow scientists to reconstruct eruption magnitude, duration, and intensity. The largest events reshaped continents subtly, altering drainage patterns, creating new lakes, collapsing hills, and reshaping basins. Landscapes bear scars, but not absence, presence transformed. You allow your imagination to drift over these deposits. Fine ash layers coat distant forests, settle into valleys, and carry nutrients long after the eruption. Iron-rich ash feeds soils in later centuries. Minerals released from volcanic glass enrich ecosystems over decades and centuries. Life is resilient, nourished by what once seemed destructive. Even the climate remembers. Aerosols reflect sunlight. Atmospheric chemistry shifts. Seasonal cycles modulate the impact. Scientists study ice, sediment, tree rings, and corals to reconstruct these subtle changes. Evidence comes from multiple lines, converging gently, revealing a history both eventful and comprehensible. You sense how interconnected everything is. One eruption can influence weather patterns across the globe. Temperatures drop by a fraction of a degree. Monsoons shift. Ocean circulation adjusts. Species respond. Feedback loops operate over years to centuries. Time becomes thick, layered, observable only through patient study. And yet, from the perspective of the Earth itself, these eruptions are just part of long-term cycles. Magma accumulates, pressure builds, energy is released, landscapes adjust, ecosystems transform. The Earth is not vindictive. It is systemic, rhythmic, patient. You now reflect on cause and effect, not as drama or fear, but as gentle unfolding. Ash does not destroy, it changes light. Cooling does not annihilate, it shifts growth. Eruption does not end life, it writes a chapter in evolution and adaptation. Each effect is a ripple, each ripple interacting with others to produce complex patterns over time. You notice the beauty in this slow interconnection. Life and rock, atmosphere and ocean, ice and soil, all carrying memory, all responding, all participating. Past supervolcanoes are teachers, writing lessons in sediment, ash, ice, and fossil. They speak of magnitude and duration, of balance and adaptation, of transformation without absolute ruin. And as you imagine the world during these ancient events, skies veiled, rivers carrying ash, forests and oceans adjusting quietly, you begin to see that while supervolcanoes can change the world, they also remind us of resilience, that ecosystems, species, and even human ancestors found ways to adapt, survive, and continue the story. Transformation, not catastrophe, is the underlying narrative. You feel a soft connection between these ancient events and the careful monitoring of today's sleeping giants. Patterns repeat. Signals whisper. Records accumulate. Knowledge grows. History guides observation, and observation nurtures understanding. You lift your gaze now from the ground and enter the realm of tools, the instruments humans have created to extend their senses beyond what flesh alone can perceive. If the Earth speaks in tremor, gas, heat, and motion, then these instruments are the ears, eyes, and touch that allow listening across scale and distance. Imagine satellites drifting silently above the planet. Each one orbits in its own path, equipped with sensors that measure light, heat, and shape. They carry radar pulses that bounce back from the Earth's surface, infrared eyes that sense warmth, and cameras that capture landscapes from angles impossible to reach on foot. From these orbits, the subtle rise or fall of a caldera basin can be detected, millimeter by millimeter, over months and years. Below the surface, seismometers listen with incredible sensitivity. They rest quietly in the soil, attached to bedrock, recording vibrations too faint for human perception. Each movement, a grain of sand shifting, a crack propagating, a fluid moving, is converted into data lines that scroll like heartbeat traces across screens. When dozens or hundreds of these devices work in unison, patterns emerge. Swarms, tremors, tremor pulses, the underground music of magma is revealed. GPS stations are another layer. You imagine each station anchored firmly in rock, sending precise signals to satellites above. Even the tiniest motion, a fraction of a centimeter, can be detected, revealing how the crust is inflating, sinking, or tilting. These stations are patient witnesses, recording slowly but faithfully, day and night. Gas sensors extend human nose. Some are stationed near fumaroles and hot springs. Others sample soil gases. They detect carbon dioxide, sulfur compounds, and other volatiles released from magma or heated groundwater. Changes in concentration, ratios, or flow rates hint at movement below. Each exhalation of the Earth becomes part of the data story. Hydrothermal monitoring adds another voice. Temperature sensors track spring temperatures. Water chemistry analysis reveals shifts in mineral content. Even subtle changes are noticed, measured, and recorded. They are clues about pathways and pressures underground. All these instruments, satellites, seismometers, GPS stations, gas analyzers, and water monitors, together form a quiet constellation of vigilant networks stretching across continents. Their collective gaze allows scientists to observe the otherwise invisible life of a supervolcano system. They watch not to control, not to provoke, but to understand and prepare. Data from these instruments flow into research centers around the world. You imagine servers quietly humming, lines of numbers cascading like starlight along cables and through software pipelines. Analysts sort, filter, and interpret. Algorithms flag anomalies. Visualizations form patterns, graphs, color maps, waveforms, translating raw numbers into insight. Each signal is preserved, compared against history, and weighted against other signals. You see that watching is a gentle act. It is a patient devotion, a combination of curiosity, caution, and care. The instruments are extensions of human attention, tools to perceive what the planet cannot reveal to unaided senses. Observation becomes an intimate relationship with the Earth, a dialogue without words. You picture real-time monitoring dashboards. Lines wiggle slowly. Maps glow softly. Alerts appear when thresholds are crossed. These alerts do not scream danger, they whisper, "Pay attention here." The Earth is telling you something. But it is still you, human, thoughtful, deliberate, who must interpret, respond, and learn. Technology also allows for simulations. Computers model magma movement, ground deformation, and gas release, exploring scenarios under different conditions. Probabilities are assigned. Outcomes are simulated. But even the most sophisticated models cannot claim certainty. They are experiments in understanding, like sketches of a landscape under shifting light. They suggest, they inform, they guide, but they do not decree. Observation networks also include field teams, geologists, geophysicists, chemists, and technicians. They visit the calderas, sample rocks, measure springs, inspect instruments, and record observations. Their human presence complements the silent sensors. Machines see, but humans contextualize. Machines measure, but humans interpret. You imagine a team walking across a caldera floor at dawn. Mist rises from the ground. Steam curls from vents. Footsteps crunch on soil. Instruments hum quietly nearby. Scientists pause, measure, and note. They are witnesses, not intruders. Their attention is a form of protection. Communication is part of the care network. Data is shared internationally. Alerts and updates move across borders and institutions. Collaboration allows expertise to spread. A geochemical anomaly in one region can be compared to patterns elsewhere. A tremor swarm in one caldera can be interpreted in light of decades of study from others. Knowledge accumulates slowly, methodically, patiently. You breathe in the rhythm of this work. Observation does not demand action, only awareness. Awareness does not demand fear, only understanding. Understanding allows for preparation. Preparation, in turn, fosters calm. Sometimes, instruments detect changes that may signal unrest, uplift accelerates slightly, tremor patterns intensify, gas ratios shift. Even so, the Earth is patient. Not every change is eruptive. Not every anomaly is catastrophic. Often, systems adjust quietly, releasing pressure in ways that never reach the surface. The network witnesses these adjustments, recording lessons without alarm. The act of watching itself becomes a meditation. You can feel the patient presence of the instruments, the careful attention of scientists, the flow of data, the rhythm of the Earth. It is a symphony composed of small, consistent acts, measuring, recording, analyzing, learning. Harmony emerges not from noise, but from persistent observation. Technology becomes a bridge between human awareness and geological timescales. Human life is short. Decades, a century, maybe two. These are tiny in comparison with the cycles of supervolcano systems. Instruments, satellites, and models extend perception beyond the immediate, allowing us to witness processes that unfold over millennia. They slow down time in a sense, making invisible motion visible, subtle pressure tangible, silent change comprehensible. You imagine yourself standing in a quiet observatory, screens before you, graphs scrolling, lines moving. You do not feel urgency or alarm. You feel attentive presence. You understand that to watch carefully is to care. Curiosity becomes stewardship. Knowledge becomes protection. You also see that observation is never complete. There are gaps in data, uncertainties in interpretation, blind spots in coverage. This incompleteness is not failure, it is humility. It reminds you that listening, truly listening, requires patience and acceptance of limits. It is enough to be aware, to notice, to learn. And as your mind drifts over the constellation of instruments, satellites, and observatories, you begin to appreciate a quiet paradox. Technology, often imagined as domination over nature, here becomes a way of aligning with it. Through tools, humans tune their senses to the rhythm of magma and stone, extending care across space and time. You realize that every measure taken, every monitoring station installed, every satellite launched, every sample analyzed is an act of attentive love for the Earth. You feel the guardianship inherent in careful observation, the humility in acknowledging uncertainty, and the compassion in striving to understand. You see that watching is, in itself, a protective gesture. And as you drift in thought among these silent, vigilant observers, the instruments, the networks, the scientists, you may begin to wonder how this careful attention transforms human perspective, how, by watching the restless Earth with patience and curiosity, we learn not only to measure the future, but to live calmly within it. You now take a slow step back from instruments, satellites, and data streams. You rest not in numbers, graphs, or simulations, but in perspective. The Earth is restless beneath you. Yes, its crust shifts, magma moves, pressures rise and fall, but this restlessness is the normal rhythm of a living planet. It does not demand panic, it demands attention and understanding. You begin to see that calmness is not the absence of motion, but the presence of comprehension. Imagine standing in a quiet landscape. Perhaps it is a caldera, broad and serene, with gentle hills and subtle rises. The wind moves softly across the soil. Birds shift in their morning flight. From this vantage, you can feel the pulse of the Earth beneath your feet. Not as threat, not as looming eruption, but as life expressed in slow, patient cycles. Tremors, deformation, gas emissions, these are whispers, not shouts. They are the language you have been learning, the quiet conversation between rock, magma, and human awareness. You remember how the Earth keeps records, ash layers, crystal zoning, isotopes in ice cores, and how past eruptions tell stories that span millennia. These records reveal that supervolcanoes are rare events. Their timing does not follow human lifespans or the rhythm of centuries. The most powerful eruptions may occur tens of thousands, hundreds of thousands, or even millions of years apart. In this vast temporal perspective, daily life, seasonal changes, and even human history are fleeting moments. You feel the reassurance that the timescale of risk is broader than your immediate experience. Urgency softens, fear diminishes. Preparedness becomes a companion to calm. Knowledge and observation are your tools. You understand that scientists monitor volcanoes diligently, observing seismic activity, gas emissions, deformation, and hydrothermal chemistry. Each signal is weighed carefully, probabilities are calculated, and thresholds are noted. This vigilance transforms uncertainty into a manageable spectrum, not a source of dread. Awareness is comfort, not alarm. You imagine communities living near known calderas. They are aware, informed, and prepared. Emergency plans exist. Communication lines are ready. Infrastructure is designed with resilience in mind. These measures are quiet acts of care, a blending of human insight and respect for natural systems. People do not live in fear, they live in harmony with understanding. Risk, you realize, is nuanced. Not all signs of unrest lead to eruption. Many signals, swarms of earthquakes, slow uplift, increased gas emissions, may subside without consequence. The Earth adjusts itself in countless minor ways, releasing pressure gradually, finding equilibrium. Nature is patient. Most unrest is resolved without dramatic events. The rare eruption is framed not as inevitability, but as one possibility among many. Your mind drifts to the cycles of observation. Instruments record continuously, satellites track from above, analysts and scientists interpret patterns. Every anomaly is noted, every trend followed. And yet, life continues around the volcano. Plants grow, animals forage, rivers flow. You sense the delicate balance between alertness and acceptance, between vigilance and tranquility. You reflect on how humans perceive danger. Instinct often magnifies uncertainty, making distant or improbable events feel immediate. Awareness shifts perspective, it stretches time, contextualizes scale, and softens emotion. The restless planet is not a menace, it is a system. Understanding reduces anxiety, transforming potential fear into contemplative curiosity. You imagine the Earth's restlessness as a slow, breathing rhythm. Magma rises and falls. Rocks adjust. Gas escapes. Heat flows. This rhythm is ancient, vast, and measured. By aligning with it, by observing, interpreting, and learning, you cultivate a sense of grounded presence. You become part of the dialogue, attentive without being alarmed. Communities benefit from this understanding. Education in geology, monitoring programs, and accessible scientific communication allow people to engage without panic. Awareness fosters resilience. Knowledge becomes a shield, not a burden. Each informed decision, evacuation planning, construction practices, environmental monitoring is a meditation on foresight and care. You picture a gentle evening near a dormant caldera. The sun dips low, painting the sky in muted golds and blues. Shadows stretch across the landscape. Instruments rest quietly, satellites continue their orbits, scientists review data with soft focus. Life persists naturally, plants sway, small animals stir, winds carry the sense of the land. The world is active, yet calm. The tension is subtle, the energy immense, but it is contained, known, and observed. Your own breathing slows as you internalize this rhythm. You feel a parallel between the Earth's subtle pulses and the slow cadence of your own heartbeat. Just as scientists interpret signals with patience, you interpret thoughts and sensations with gentle attention. Awareness and understanding become tools of tranquility, aligning your internal state with the measured, patient motion of the planet. You reflect on probability, a concept that softens certainty into understanding. Scientists do not predict exact eruption dates. They estimate ranges, watch for converging signals, and assign likelihoods. In this uncertainty, there is no chaos, only the richness of possible outcomes, each with context and history. Probability provides clarity, not alarm. You imagine the planet as a vast, living clock. Its mechanisms operate over millennia, not minutes. Supervolcanoes, earthquakes, and climate shifts are hands moving slowly across an immense dial. Human perception is brief in comparison, but it can be aware. Watching, understanding, preparing, these are acts of alignment with a larger temporal rhythm. Preparedness also includes emotional awareness. You recognize that uncertainty need not trigger fear. By understanding context, timescale, and probability, you cultivate a mindset of curiosity and respect. You accept that some aspects of nature are beyond control, and that this acceptance is itself a form of calm strength. As you walk in your imagination along the gentle slopes of a caldera, you notice the interplay of stillness and potential. The land is serene, yet layered with history. Beneath your feet, magma rests in chambers, adjusting quietly. Rocks bear stress, moving subtly. The surface seems calm, but it carries memory and motion. You do not feel threatened. You feel attuned. You imagine teaching these ideas to others. You would explain that living on a restless planet is not about constant vigilance or fear, but about understanding rhythms, paying attention to signals, and respecting natural systems. Preparedness, knowledge, and calm observation allow life to flourish even where the Earth's pulse is strong. This perspective fosters security, not complacency. Your mind drifts to personal reflection. You consider your own responses to uncertainty in daily life. How often do you feel urgency where patience is more appropriate? How often do you react to small signals as if they are immediate threats? Observing the Earth teaches you a lesson about yourself, the value of measured attention, of gentle analysis, of aligning perception with reality rather than instinct alone. You sense a connection between planetary cycles and human cognition. Both require observation, interpretation, patience, and reflection. Both operate on multiple timescales. Both respond to cumulative signals rather than single events. You feel grounded in this analogy, understanding that calm awareness is a skill as vital as any instrument. Even in places of known geological activity, daily life continues. People live, love, work, and play. They garden, hike, and walk dogs along trails. Schools operate, markets open, festivals continue. Restlessness does not negate continuity. Awareness preserves life, fear erodes it. You breathe slowly, letting this sense of balance permeate your body. You visualize instruments quietly monitoring, data streaming softly, scientists interpreting patterns, communities informed and prepared, ecosystems adjusting naturally. The Earth's restlessness is not chaos. It is order expressed in long cycles. Understanding is the lens that softens perception. You feel a sense of connection to the past, the present, and the future. The lessons of ancient eruptions, the patient work of monitoring networks, and the gentle rhythms of living systems merge into a continuum. You rest in the knowledge that being attentive, informed, and mindful allows coexistence with a planet that is never perfectly still. And as your awareness settles, you realize that calmness is a choice as much as it is a state of understanding. By observing, learning, and respecting the Earth's rhythms, you create a mental space of serenity within which life can unfold safely. The restless planet becomes a partner in life's continuity, not an adversary. And in this quiet, reflective space, you begin to sense the slow, patient cycles of renewal and release, the long clock of stone and fire that moves beneath and through time, reminding you that understanding and observation allow you not only to live safely, but to feel peacefully grounded, even on a restless world. You draw a deep breath and step back to see the Earth in its full, slow grandeur. From the restless movement beneath calderas to the drifting ash of ancient eruptions, from the careful instruments that watch today to the lessons stored in rock and ice, everything fits into a rhythm far beyond human lifetimes. You begin to feel the scale of geological time, immense and patient, where centuries and millennia are moments, and millions of years are the measured heartbeat of the planet. Imagine the Earth as a living clock. Its hands are made not of metal, but of stone, magma, ice, and water. They turn slowly, imperceptibly to those who stand on the surface for only a brief moment. Each cycle, uplift and subsidence, eruption and quiet, erosion and deposition, is a tick, a silent reminder of continuity. In this long clock, supervolcanoes are rare beats, large and profound, but they are only part of the ongoing rhythm. Life continues to flow around them, as it has for millions of years. You allow yourself to drift across these immense spans of time. You think of Yellowstone, Toba, Campiflagrii, Taupo, each a sleeping giant with a history written in ash, lava, and caldera. Their previous eruptions reshaped landscapes, altered climates, and transformed ecosystems. But after each eruption, life returned, soil recovered, forests grew, rivers reshaped themselves. The planet's cycles are forgiving in their persistence, showing that destruction and creation are threads of the same tapestry. Supervolcanoes remind you of power, but also of patience. Magma collects over tens of thousands of years. Crust bends slowly. Pressure builds in a gentle, incremental way. The Earth does not rush. Its processes are deliberate, extended, almost meditative. And in this patience, there is security. It is rare that events happen suddenly without warning. Observation and understanding allow humans to anticipate changes over timescales that are meaningful in planning, even if not precise in day-to-day timing. You feel yourself stepping gently into this rhythm. Just as the Earth moves slowly and deliberately, you slow your own mind. Each inhale is measured, each exhale expansive. Your thoughts follow the cycles you have studied: energy accumulation, subtle signals, release, renewal. You are attuned to the deep pulse beneath the crust, even without instruments. You carry in your own body the echo of the planet's slow timing. This awareness brings humility. The long clock of stone and fire dwarfs human history. Civilizations, cities, and even nations are fleeting in comparison. And yet, humans have found ways to coexist with these cycles. Observation, measurement, and respect allow safety without fear. Understanding allows presence without anxiety. You recognize that you are part of this continuum, small, fleeting, but attentive. You imagine standing on a high caldera rim, watching clouds drift across the sky, feeling the cool wind on your skin. Below, the landscape is tranquil. Rivers meander, forests stretch in quiet persistence, and subtle uplift hints at the process is moving unseen. You feel connected to this pulse, not as an intruder, but as a participant in the patient dance of geological time. Cycles are everywhere. Rocks erode, depositing minerals in distant valleys. Water carries these minerals, nourishing ecosystems far away. Volcanoes erupt, temporarily changing climate, then ecosystems adapt, recover, and continue. Mountains rise slowly, rivers carve deeply, and the crust flexes and bends. Each motion is a piece of the ongoing clock, each change recorded subtly, leaving traces for future observers. Time is layered, overlapping, intricate. And in this awareness, you realize the lessons of prediction. Supervolcanoes cannot be predicted like the strike of a clock at noon. But understanding their rhythms allows you to live with confidence. You know which patterns matter, which thresholds signal attention, and which motions are simply part of the background hum of Earth's processes. You understand that certainty is rare, but knowledge and patience are always available. You consider human curiosity, extended through observation and technology. Satellites orbit silently, GPS networks measure movement, seismometers listen, gas analyzers detect whispers of volatile escape. Researchers analyze data with care, constructing models that explore possible outcomes. And through this collective effort, humans participate in a dialogue with a planet whose scale is vast and whose tempo is slow. Watching, listening, understanding, these are acts of stewardship, gentle but profound. Reflection brings comfort. You see that the Earth's restlessness is not a source of panic, but a framework for wonder. Each tremor, each uplift, each eruption is an invitation to observe, to learn, to attune. Supervolcanoes, while powerful, are part of a natural system that has operated for millions of years. Their cycles remind you of continuity, resilience, and adaptation. You breathe deeply, letting the magnitude of these rhythms fill your awareness. Time stretches around you. You feel small, yes, but also integrated, a conscious observer within a planet whose pulse is steady, vast, and measured. Life's fragility is tempered by persistence. Change is constant, but so is adaptation. The long clock of stone and fire continues, uninterrupted and patient. You imagine the world far into the future. Humans may come and go, but the cycles endure. Volcanoes will rise and fall, ice sheets will wax and wane, mountains will erode, and rivers will carve new paths. Life will adjust, persist, and evolve. The Earth does not hurry. Its timing is generous. In this generosity, you find peace. Prediction, you realize, is not about exact dates or catastrophic events. It is about understanding the interplay of forces, recognizing patterns, and aligning with cycles that unfold over centuries and millennia. In this light, uncertainty is not threatening, it is a reflection of the immense scale and complexity of life and the planet. To know is to respect. To respect is to live calmly within the rhythm of time. As night falls in your imagination, you picture the quiet caldera beneath a starlit sky.